And we're now recording. I tried to share the screen. Let me see if I can get it to work. Okay. So we're somewhere around here. Okay, so we're in 5.3. Tomorrow you have a quiz which will take up a lot of the class period. So I was going to give you a huge chunk, I'd say half an hour or more to do the quiz. It's going to be of the type where you do a left sum, a right sum, and a midpoint sum. I'll give you a function. You chop it up into so many pieces, and you complete the left sum, right sum, and midpoint sum. Again, for the exam on the 20th, I will likely not have you do all three of them. I might have you just do one of them, but at least for a quiz like this, I want to be able to see that you can do all three, a left sum, a right sum, and a midpoint sum. Okay, so that'll be tomorrow. Right, so reminder, looks like I might be able to finish early. If I finish early, I'll just go ahead and start reviewing for the final. Wednesday, the 19th, you may have a question and answer session for this particular test. Okay, then Friday, the 21st, we'll continue to, 21st, continue to review for the final. Now, I'm not promising you I can get you back your test the very next day, but I should have it to you by the weekend like I normally do. Okay, but I would try to have at least a solution video so you know how to study for the final. Okay, so again, a final exam, Monday the 24th, 8:10 to 10:40. Please notice the starting time is 8:10, not 9:10. It's school policy. Now, if you want to join it at a regular starting time of 9:10, I'll let you, but I have to stop at 10:40. Besides, I'm giving another exam that day, so I can't go past that school rules. Okay, so you have 2.5 hours. Just bring all your former cheat sheets. So the cheat sheet from the first test, second test, third test, fourth test, and the fifth test, which you're still working on. Just bring them all. You're allowed to bring them all. You don't have to rewrite them all. Just bring them all. Now, if you lost it, you threw it away, then you'll have to make it up again. But you can have 5 formula sheets for the final exam, 1 for each test. Okay, and the best way to study for the final exam is just study the old exams. Okay, so I will do something like I'll pick 3 questions from every test. 3 times 5 is 15, and that'll be the final exam, something like that. Or maybe 4 questions, and then 4 times 5 would be 20. Okay, again, they don't have to be the very same questions, but questions that are very similar to what we've already seen in previous exams. Okay. All right, so that's what's happening. Any quick questions about that before we start? I'll check the chat. Okay, I don't see anything there. All right, so we'll continue on with the fundamental theorem of calculus, part 1, and then we'll go to fundamental theorem of calculus, part 2 also. All right, so fundamental theorem of calculus, part 1. Page 394. F is continuous on a closed interval from A to B. G is defined to be this area function. G of x is the integral from A to x, f of t dt. Notice it's a constant on the bottom, variable on the top. Okay. Then the G is continuous on the closed interval from A to B, differentiable on open A, B, and G prime of x is equal to f of x. Okay. In essence, all you do, just pick this up, put it right there. Okay. So I was getting to the problems at the end, 59, 61, and 63, find a derivative of the function. So notice 59, integral from 2x to 3x, 61, x to x squared, 63, cosine x to sine x. So we know how to do constant to a variable. We know how to do variable to a constant. Now, what if there are 2 constants? So notice the hint they give you after 59. Integral from 2x to 3x can be thought of as the integral from 2x to 0. So where does 0 come from? You can just make it up. You can put any number that you want. Plus the integral from 0 to 3x. And we know how to do each of those. So that is using this property. Figure 15 on page 387, right? Let me show you both. integral from A to C, dark blue, plus the integral from C to B, light blue, is the same as the integral if I went straight from A to B, same amount of area. Okay. So that'll take us through the rest of that type of problem. And then let me show you those, and then we'll go to FTC2, Fundamental Theorem of Calculus, Part 2. All right, so here we go. Let's knock these off. All right, give the derivative of g of x. Remember, we're actually finding a derivative, although you're not really differentiating u squared minus 1 over u squared plus 1 or whatever. Okay, it's just a matter of plugging in. Okay, so what happens if you have a variable and a variable? Okay, so we go integral from 2x to 0, and then from 0 to 3x. This is good to go. Constant, variable. This is not good to go. Variable, constant. So we know what to do from yesterday. Switch this around and put a negative. Right, negative integral from 0 to 2x of u squared minus 1 over u squared plus 1. And then this is good to go. All right, so I just add the two. The derivative of a sum is the sum of the derivatives. So I differentiate this, differentiate this. Okay, so we know the way the game works. Plug in 2x right there, and then times the derivative of 2x, which is 2. Then over here, plug in 3x right there, and then times the derivative of 3x, which is 3. Okay, that's all. So here we go. Negative, put 2x right there, 2x squared minus 1 over 2x squared plus 1 times the derivative of 2x, which is 2. Okay, and likewise over here, plug in 3x right there, 3x squared minus 1, 3x squared plus 1, and then times the derivative of 3x, which is 3. Okay, then just a little bit of cleanup. So negative 2, this is 4x squared minus 1 over 4x squared plus 1, plus 3 times 9x squared minus 1 over 9x squared plus 1. And there we go. Okay, I actually have 61 on another paper, so I'll go jump out of order here, do 63 next. Doesn't really matter that much. So y equals integral of cosine x to sine x, natural log of 1 plus 2v dv. So same trick. How do I integrate from cosine x to sine x? I go from cosine x to 0. Technically, it doesn't have to be 0. It could be any real number, but might as well just pick 0. And then integrate from 0 to sine x. This one's good, constant, variable. This one is not good, it's variable, constant, so we know what to do. Switch this around and put a negative. So negative, integral from 0 to cosine x, integral from 0 to sine x. Okay, so now it's good to go. So don't forget the minus, it's easy to forget the minus sign. So cosine x goes right there, and then by the chain rule, multiplied by the derivative of cosine x, which is going to be negative sine x. And over here, for the derivative, just put sine x right there where you see the v, and then multiply by the derivative of sine x, which is cosine x. So here we go. Y prime is temporarily negative, ln 1 plus 2, and then replace v with cosine x. And then by the chain rule times the derivative of cosine x, which is negative sine x. And there's a double negative. There's a negative there, a negative there. So in red, I change it to a positive. Plus natural log 1 plus 2 v put in sine x. And then by the chain rule times the derivative of sine x, which is cosine x. Okay, so that's pretty much about it. All I did after that was clean it up and made that all positive. So final answer, natural log of 1 plus 2 cosine x times sine x plus natural log of 1 plus 2 sine x times cosine x. Okay, so this is fundamental theorem of calculus part 1, as it were. Okay, I'm about to do fundamental theorem of calculus part 2. So let me at least do the focus thing over here. Okay. And then 61. Then I'm done with FTC 1, fundamental theorem of calculus part 1. 5.361. capital F of x is the integral from x to x squared of e to the t squared dt. Okay, so variable here, variable here. All right, so to go from x to x squared, I go from x to 0 and then 0 to x squared. This is good to go, constant variable. And for these kind of problems, it's always going to be that way. The second one is already good to go because it's already a constant here, variable here. The first one is always the one that's got to be switched, right? Because it's a variable here and a constant here. So we know what to do, switch it. So the 0 is on the bottom, x is on the top, and a negative. And now they're both good to go. Okay, so here I put the x right there, and essentially that's it. Or you could say the chain root, but the derivative of x is 1. Then here you put x squared right there, but then you have to multiply by the derivative of x squared, which is 2x. Right, so here you go. F prime of x is negative e to the x squared. And you don't really have to worry about the chain root. It was just a single letter, x. Or again, if you want to think of the chain root, say, okay, multiply by the derivative of x, but that's just 1. So negative e to the x squared. It was just like the previous problems we did yesterday, right? You just simply substitute in. Here's the chain root. So e to the, replace t with x squared, so it's x squared squared. And then by the chain root times the derivative of x squared, which is 2x. Okay, so a little bit of cleanup. Negative e to the x squared plus 2x e to the x to the 4th. And that's it. So that's fundamental theorem of calculus part 1. I'm now finished with FTC1, and I'll get started with FTC2, fundamental theorem of calculus part 2. And let me just do the quick focusing thing for this, and then that's about it. Right. So let me see. Don't see any questions in the chat. Yeah, if you have any questions, put it in the chat. But now we're ready for fundamental theorem of calculus part 2. Okay. To be honest with you, FTC2 is the more useful of the two. Okay. In fact, you're going to be using fundamental theorem of calculus part 2 for the rest of this class, but it's going to be prominent through Calc 2. It'll be all throughout Calc 3. FTC1, we basically don't use it anymore. You need FTC1 to prove FTC2. And then once we prove it, then we say, forget about it. Okay, on page 398, there's FTC2. You can put it down if you want to. But again, if we were meeting face-to-face, you should memorize it. It's really not that hard to memorize, though. But integral from a to b of f of x dx is capital F of b minus capital F of a, where capital F is any antiderivative of little f. That is, capital F prime of f is equal to little f. Okay, I will show you the derivation or the proof that that works. Okay, you're not responsible for the proof. I'm responsible for the proof. You're just responsible for using the theorem. Okay, so I'm going to run through a derivation of the proof of the fundamental theorem of calculus part 2. Okay, and let's see. It shows up by itself on page 396. So here it is again, but it's essentially the same as before. Okay, if little f is continuous on the closed interval from a to b, integral from a to b of f of x dx is capital F of b minus capital F of a, where capital F is any antiderivative f of little f that is a function such that capital F prime is equal to little f. Okay, let me run through the proof of that. And this is a very powerful theorem. What it essentially means is that when we were having those functions and we were chop, 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 and draw a rectangle, and base times height, all those Riemann sums, which you will do in the quiz tomorrow. You did the left sum, the right sum, and the midpoint root. Okay, there's a lot of work, and it was only an approximation. This makes it way easier. Not only is it way easier, we're going to get the exact answer, not an approximation, because we're doing rectangles, not a little bit off kind of approximation. This will give you the exact answer. All right, so here's the derivation of the proof. From FTC1, fundamental theorem of calculus part 1, if g of x is the integral from a to x of f of t dt, where f is continuous, constant here, variable here, then g prime of x is f of x, right? That means the language is g is an antiderivative of little f, right? If g prime of x is f of x, that means g by definition is an antiderivative. The derivative of g is f, that means g is an antiderivative of f. Now, let capital F be any antiderivative of little f. We know that it exists. There has to be at least one because we already found little g, okay? So there's at least one. There's actually infinitely many. But we know the way antiderivatives work. G is an antiderivative. Capital F is also an antiderivative. That means from section 4.9, G and F, capital F, differ by a constant C. Right? That is, G of x is capital F of x plus C. Okay, one more time. This is an antiderivative. This is an antiderivative. Therefore, they differ by a constant. Right? It's just like when I say, what's the integral or antiderivatives of x squared? Say x cubed over 3 plus C. Okay, so that means an antiderivative of x cubed over 3. Another one is x cubed over 3 plus 1. Another one is x cubed over 3 plus 2. Another is x cubed over 3 minus a million, and so on. Right? So if little g is an antiderivative, capital F is any antiderivative, that means they have to differ by a constant. G of x is capital F of x plus C. Now I'm going to plug in A. Okay. X is a variable. It works all the time. So if it works all the time, it has to work when I plug in A. G of A is capital F of A plus C. But G of A is 0. Look at the way G of x is defined. It's the integral from A to x. So if I plug in A, I'm integrating from A to A. How much area is there from A to A? Well, 0. G of A is 0. That means I can replace this with 0. 0 equals capital F of A plus C, or subtracting over. C is equal to negative capital F of A. Okay. C is negative capital F of A. I can plug that back over here. So G of x is capital F of x minus capital F of A. Now I'm going to plug in x equals b. Put a b right there, put a b right there. G of b is capital F of b minus capital F of A. Okay, and what is G of b? From the way it was defined, G of b means I just put a b right there. Integral from A to B of f of t dt is capital F of b minus capital F of A. Okay, and that's correct. But notice right here, this thing no longer has the variable x. So since there's no longer an x, I can go back and say f of x dx. And here's FTC part 2. Okay, and this finally ties together 4.9 when we were doing all the antiderivatives and section 5.1 and 5.2, which seem to be totally different. Okay, integral from A to B of f of x dx is capital F of b minus capital F of A. That's fundamental theorem of calculus part 2. That's what I want you to know. And again, if we were meeting face to face, I'd make you memorize it. You really should memorize it. And it's really not that hard to memorize. Okay. Now, you are not responsible for all this. I'm responsible for all this. Okay, but I'm responsible to at least show you where this came from. It isn't like someone just pulled it out of a hat. Here's a derivation of it. Okay, so now we know if I don't have an a and a b, integral of f of x dx, the answer is going to be blah, blah, blah plus c, section 4.9, right? Anti-differentiate plus c. Then we had a definite integral, and we were doing, 2 sections, section 1, section 2. We're saying it seems like we have a brand new different meaning of this. It's the true area, assigned area, SIGNED, where the area above the x-axis is positive, area below the x-axis is negative. It seems like it's totally different. Now it isn't. Okay. So what this means is the definite integral, the signed area, is exactly capital F of b minus capital F of a. So we're going to anti-differentiate, integrate, plug in the top number, plug in the bottom number, and subtract. This theorem says that will be the exact answer, not an approximation. Okay, very strong theorem. And furthermore, the theorem says you can pick any antiderivative. Since you can pick any antiderivative, the easiest one is where the constant is 0, right? Remember we were doing blah, 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 plus c? The theorem says f can be any antiderivative. It can be blah, blah, blah plus 1, blah, blah, blah plus 2, blah, blah, blah minus 2, blah, blah, blah minus 1,000,000. What's the easiest constant to pick? 0. Okay, which means when you do definite integrals, you don't have to put the plus c. For indefinite integrals, you need the plus c, but not for indefinite integrals. Okay, very powerful theorem. And that's the way it always is in calculus. Remember when we were first doing derivatives? You were doing limit h approaches 0, f of x plus h minus f of x all over h. Chapter 2, say, man, this is long and tedious. It'd be nice to have shortcuts. Okay, so once you get your lumps, so to speak, then we give it a shortcut. We're doing the exact same thing with integration now. Okay, so at first, right, we took a curve and we chopped it up into so many pieces and went base times height, which you'll still have to do tomorrow for the quiz. And you did L sub n, R sub n, M sub n. So chop up into so many pieces, n is equal to 4, n is equal to 5 or whatever. And then form your rectangles by doing the left endpoints, right endpoints, or midpoints. Okay. That's the hard way. Now the easy way, integrate, plug in the top, plug in the bottom, subtract. Okay. The theorem says you can pick any antiderivative. So the easiest to pick is where the constant is 0. Okay. And that will be the exact value, not an approximation, the exact value of the integral. Very strong theorem. Okay, so the rest of today, I'll show you some examples of that. We'll do tomorrow, but then tomorrow, of course, I want to make sure I give you enough time to do the quiz. Okay, so FTC2, Fundamental Theorem of Calculus Part 2, is the rest of the problems in the homework on page 400. That would be 19 through 41, I think it is. All right, so integral from 1 to 3, x squared plus 2x minus 4 dx. That means we don't have to take the interval from 1 to 3, chop, 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 chop it up into 4 pieces, 8 pieces or whatever, form rectangles, base times height, and all that stuff. Okay. Instead, we integrate, anti-differentiate, like so. Okay, we already know how to do this from 4.9. So what's the integral of x squared? X cubed over 3, power root, right? Integral of 2x to the 1 is 2x squared over 2. 2's cancel out, you have x squared. Integral of -4, -4x. How can you always check your antiderivative? Take the derivative, right? So, I wonder if I integrated correctly. Take the derivative. What's the derivative of this? Right? 3 comes down, knocks off the 3, and you have x squared. Derivative of x squared is 2x. Derivative of -4x is -4. It works. And you don't need the plus c. Okay. That's why in the theorem, we proved it for any antiderivative. This formula works for any antiderivative. What's the easiest antiderivative? Well, if the constant is 0, right? Yeah. Now, here's a notational convention. I want you to use this notation. So if I don't see the proper notation, I can still take off points. Okay, the funny looking S moves over to the right side and straightens out. It's almost as if to say, okay, if you have the curve S on the left side, and you take the time to go through the trouble of putting on the right side and drawing that straight line there, we know you're talking calculus. We know you're doing the fundamental theorem of calculus part 2. Okay, so no longer is on the left side. After you integrate, it migrates over to the right side and straightens out. 1, 3. Okay, what's this capital F of B minus capital F of A stuff? It means plug in 3 in parentheses, minus parentheses, plug in 1. That will be the true value of the integral. Okay, so plug in 3. 3 cubed is 27. 27 divided by 3 is 9. Plus 3 squared, which is 9. Minus 4 times 3, which is 12. Minus plug in 1. 1/3 plus 1 minus 4. Grind it all out. That will be the exact value of this integral. Okay, so what did I do here? 9 plus 9 is 18, minus 12 is 6. And then I decided to distribute the negative. I don't want to do too much at once. So minus 1/3, minus 1 plus 4. Okay, so 6 minus 1 plus 4 is 9. 9 minus 1/3, 8 2/3. The exact value is 8 2/3. Pretty amazing concept. Okay, so if I actually did my Riemann sum, if I went from 1 to 3, chop, 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 and did, either the left endpoints, right endpoints, or midpoints, I'd probably get something close to 8 2/3, but not exactly. Maybe it'll be 8.5, maybe it'll be 9 or whatever. I have no idea. Okay, and of course it depends on your n. By doing this, I don't have to do any of that Riemann sum, chop it up into so many pieces. And furthermore, I got the exact answer. Okay, pretty powerful. Right. Okay, 23. Integral from 1 to 9 of radical x dx. Okay, before actually going on, let me show you what we're actually getting. Square root function looks something like this, right? Very crudely. Here's 1, here's 9. Okay, you can imagine chopping this up into so many rectangles, maybe n equals 4, right? If n equals 4, my delta x would be 2, right? From 1 to 9 is 8, chop it in 4 pieces. So go 1 to 3, 3 to 5, 5 to 7, 7 to 9. Okay. Get the sum formed by left endpoints, right endpoints, and midpoints, which you'll have to do on tomorrow's quiz. Okay. Make your rectangles, add them all up. Very tedious, and it's only an approximation. By doing this integration, you'll get the exact answer. Okay, so here we go. This, of course, is x to the 1/2. So the integral of x to the 1/2, power root, add 1, x to the 3/2, divided by 3/2 means times 2/3 from 1 to 9. Factor out to 2/3. Okay, plug in 9. You're allowed to factor out a constant. 9 to the 3/2 minus 1 to the 3/2. Okay, 1 raised to anything is 1. Remember how 9 to the 3/2 is interpreted? It means square root of 9, 3. And then 3 cubed, 3 times 3 times 3 is 27. 27 minus 1 is 26. 26 times 2 over 3, 52 over 3. Which is what, 17 1/3? What does that number represent? The exact area under the curve of y equals square root of x, bounded by the x-axis between 1 and 9. Not an approximation. The exact area is 52 over 3. Pretty strong theorem, as I think you can see here. Okay. All right, I'll do a few more here. See how much I'm willing to do. Okay, jump into 31. Integral from pi over 6 to pi over 2 of cosecant t, cotangent t, dt. And of course, you should know it doesn't matter what letter you pick, whether you have t or theta or w or x, okay? So what's the dt? It's not really serving any purpose except to name the variable. It will become important when we do substitution in a little while. Okay. dt is a tiny little change in t. It's delta t for very, very small delta t, or as delta t approaches 0. Okay, the integral of cosecant cotangent is negative cosecant of t, right? Because the derivative of cosecant t is negative cosecant t cotangent t, right? Therefore, the derivative of negative cosecant t is positive cosecant t cotangent t. Okay, now, I don't like to have extra negatives. I know I'm going to have to subtract. So you can always play this trick. What did I do here? How did I get rid of the negative? See what happens? Flip the 2, right? Remember, the integral from A to B is the opposite of the integral from B to A, right? So again, notational convention, I could be looking for this. So if you don't have proper notation, I could take off points. The funny looking S is on the left side before you integrate. It moves over to the right side and straightens out after you integrate. All right, so positive cosecant t, and I move pi over 6 on the top, pi over 2 on the bottom. So it's cosecant pi over 6, plug in the top number, minus plug in the bottom number, pi over 2. Okay, cosecant is the reciprocal of the sine. Okay, sine of pi over 6, 30 degrees, is a half. Reciprocal of a half is 2. Cosecant of pi over 2, sine of pi over 2, sine of 90 degrees is 1. Reciprocal is 1. So 2 minus 1 is 1. Okay, then 39 is a little bit trickier. Integral from 1 over radical 3 to radical 3, 8 over 1 plus x squared dx. I can show you the original. 39, 1 over radical 3, 8 over 1 plus x squared dx. I'm allowed to take the 8 out, take a constant out, 8 times 1 over 1 plus x squared. What's the integral of 1 over 1 plus x squared? Another way of saying that is, what function do you know of whose derivative comes out to be 1 over 1 plus x squared? Arctangent, inverse tangent. Right? The derivative of inverse tangent or arctangent is 1 over 1 plus x squared. Therefore, antiderivative of 1 over 1 plus x squared. So what about the 8? Just put the 8 in front. Inverse tangent. Radical 3, 1 over radical 3. Okay, factor the 8. So you plug in the top number. You can notice the funny looking S is on the left side. After you integrate, it moves over to the right side. It straightens out. So inverse tangent of radical 3 minus inverse tangent of 1 over radical 3. Okay. This comes out to be pi over 3. You can either memorize it or there's a sneaky way to prove that. And this turns out to be pi over 6. Okay, pi over 3 minus pi over 6 is pi over 6. 8 pi over 6 comes out to be 4 pi over 3. Okay, I'm going to digress just a little bit. I'll show you how you can come up with this. I mean, you can memorize it. By the way, you might say, have I memorized it? No, I haven't memorized it, but I know how to work it out. Okay, using the unit circle and so on. So let me take a quick time out and digress, show you how I can get this. You know, if you haven't memorized, great for you. But how do you do this if you don't have it memorized? And something happened. What happened? This thing got knocked out. Okay, I think I got so excited I knocked out the video plug here. Let me see if I can get it back. Let's see. Okay, we're back in business, I think. Okay, so a little review of trig. How do I get inverse tangent of radical 3? And you can do, once I show you this, you can do something similar for this and get pi over 6. Okay, so let me write out for you here. Inverse tangent of radical 3 call it theta. get rid of the -1. So am I taking a tangent of radical 3? No, I'm taking the inverse tangent of radical 3. I must be taking a tangent of something else. That else is theta. Okay, tangent is what trig function divided by what other trig function? Sine over cosine. Okay, write it as radical 3 over 1. Okay, and I think we may have done something like this way back in the first chapter. The trick now is to divide top and bottom by 2 because it works. Okay. And then just look over here and look over here. Okay, so I say to myself, sine of theta is radical 3 over 2. Cosine of theta is 1/2. So what angle do I know works like this? Well, that means x coordinate, cosine x coordinate is 1/2. So I go halfway across, draw my angle, and that looks like 60 degrees. Or pi over 3. So theta is pi over 3. I'll raise it up so you can see that again. Inverse tangent of radical 3 is theta. Tangent of theta is radical 3. Tangent is sine over cosine, make it radical 3 over 1. Divide top and bottom by 2. So what angle do I know of where the sine of the angle is radical 3 over 2? Cosine of the angle is 1/2. I don't like working with radical 3 over 2. I like 1/2. Cosine is x coordinate, sine is y coordinate. So I draw a rough unit circle, go halfway across, draw my first quadrant angle. It looks to me like 60 degrees or pi over 3. Okay. And yeah, you do exactly the same trick for this one. So if you do the same trick for that one, you know, divide top and bottom by 2, you end up with pi over 6. Okay. So let's see how that one goes. Okay, let's see if we have time for maybe a couple more. And that's about it. Okay, 5.3, number 33. Then you go from 0 to 1 of 1 plus r cubed dr. Okay, it doesn't matter if you have x dx or theta d theta, r dr, same thing. Now let me just go ahead and say, if this was 1 plus r squared to the third power, I could not do what I'm about to do. It's because of the chain rule. But because the derivative of 1 plus r happens to be 1, I can just go ahead and do the power rule. Which means 1 plus r to the fourth power divided by 4. Okay. You can easily double check. What's the derivative of this? 4 comes down, knocks out the 4, 1 plus r cubed. Then by the chain rule times the derivative of the inside. But the derivative inside is 1. So I'm good. Okay. I could not do that trick if this was 1 plus r squared. It's not going to be 1 plus r squared to the fourth over 4, because the beginning part would be the same. You say, well, why don't I just go 1 plus r to squared to the fourth over 4? The beginning part, 4 cancels the 4, 1 plus r squared cubed, but then times the derivative of the inside. If I had, let's say, 1 plus r squared, you'd have to multiply by an extra 2r, and that's not going to work. Okay. In fact, if you had an r squared here, 1 plus r squared cubed, the only way to do this problem is to literally multiply it all out. You'd have to figure out 1 plus r squared times 1 plus r squared times 1 plus r squared. Okay. But because the derivative of the inside is 1, I can just go straight to this. Okay, so again, the funny looking s on the left side, move it over to the right side, straighten it out, 0 to 1. It means plug in 1. 1 plus 1 is 2. So 2 to the fourth over 4 minus plug in 0, 1 to the fourth over 4. And I already have a common denominator of 4. So 2 to the fourth is 16. 1 to the fourth is 1. 16 minus 1, 15 over 4. Okay, the problem is finished, but I'll dig a little deeper. What is that 15 over 4? If I graph this function, okay, you know, it's a cubic. Plug in 0, you get 1. Plug in 1, you get 8. It curves up like that. Okay, I just do real crudely. Something like that, right? The area under the curve, 15 over 4, 4 3/4. Exactly, not approximately, exactly. Okay. Very powerful theorem. All right, last one I was going to do for today is 37. Okay, and then if anybody has any question, you can ask it, otherwise we'll quit. But I should have shown you how to do most of these problems now. 37, integral from 0 to 1 of x to the e plus e to the x. Okay, here's where you have to watch out how you anti-differentiate. X to the e, e to the x. Keep in mind, e is a number, x is not a number. It's a variable. Maybe I'll just quickly go like this. Let's get this out of the way. Do you remember what's the derivative of e to the x? E to the x. So what's the integral antiderivative of e to the x? E to the x. Same thing. How about x to the e? That's like saying x to the 2.7 whatever. That's a power root. X to the e plus 1 over e plus 1. And just leave it like that. Don't change it to 2.7. And I guess it'll be 3.7 or whatever. Just go x to the e plus 1 over e plus 1 plus e to the x. How do you check your answer? Take the derivative. The derivative of this, e plus 1 comes down, hits this e plus 1, it'll cancel out. And then you're supposed to subtract 1. You have x to the e, perfect. And what's the derivative of e to the x? E to the x. It works from 0 to 1. Okay, plug in 1. You know 1 raised to anything is 1. So 1 over e plus 1 plus plug in 1, e to the 1 is e. Minus plug in 0, 0 to anything is 0. Plus e to the 0, which is 1. So best final answer, 1 over e plus 1 plus e minus 1. Okay, that's it. Let me do the little focus thing here. And I'm almost done, except I was going to show you one more just to set you up, but I wasn't going to do it in its entirety. We'll just let you think about it. Okay. And let me double check. That would be 41. Let's see, yeah. 41, the last one of this type. 41, 2 to the s. Okay, now integration and differentiation are opposite operations. Do you recall how to take the derivative of 2 to the s? Yeah, it could be 2 to the x, we're used to it, but it doesn't matter. The derivative of 2 to the s is 2 to the s ln 2. In other words, you multiply by ln 2. Therefore, what do you think happens when you integrate? You do not multiply by ln 2. You divide by ln 2. So to integrate 41, it'd be 2 to the s divided by ln 2. And then go from there. Okay. All right, I'm done for today, folks. So tomorrow I won't lecture much at all. In fact, I may decide not to lecture at all. And you'll just have a quiz involving left sums, right sum, and midpoint rules. Okay, so anybody have any questions for today? Just about out of time. Any quick questions? Otherwise, we're done. I'll check the chat. Or you can unmute yourself. Okay, I don't see anything in the chat. Anybody join late, put your name in the chat also. Okay, I don't see anything, so we're done for the day, folks. Okay, have a good day. We'll see everybody next time. Okay, bye, everybody. Okay, Christian, I got you.